computation or chemical AI. And then I'm going to describe a little bit of chemical discovery. What is discovery? I think, Tim did a brilliant job of really telling us the reactions actually don't exist. I don't mean that in a bad way, but it's all understanding the process variables. And actually, lots of reactions exist, and it's all so reactivity is the key thing, and we'll talk a little bit about that. And then something that you may be interested in is, will computers dream of electric drugs? And this is the pull on the phrase of, will androids dream of electric sheep? That is the question about whether we could ever make an AI that's conscious. This is really about, can we actually dream up drugs that are in silico that are not only effective but makeable first time round? So wouldn't it be great if you could do an investigation, a theoretical investigation, and come up with a series of compounds and know that those compounds are makeable, not just feasible, but you can actually go to the lab and know them. It's a bit like me telling you, us arriving in Tokyo, and you've got a map of Tokyo, and maybe, I don't know if Bartosz is here, but Cynthia could tell you in chemical space what is feasible in terms of a pathway to go from A to B, but you don't know if there's some potholes in the road, if a road is closed, or maybe there's been an earthquake or something. So wouldn't it be great if you could know in real time that you're able to navigate that? And we'll talk about that. Okay, so to get into the main point of the lecture is really to just introduce one concept, that is that we need to digitize chemistry in a way that makes it unambiguous. As you've probably seen by this wonderful conference, where we've got so many incredible perspectives, are all compatible, actually. I don't think there's anyone really saying, we must do it one way and no way else. But we've got lots of people doing high throughput chemistry, thinking about computation, instantiation, maybe some theoretical analysis. What we perhaps should think about in the world of reproducibility and collaboration is, how can we make sure that the chemistry we do, be it automated or manual, be sufficiently well described that I can describe your preparation in my lab tomorrow, and you could make my new molecule in your lab tomorrow, and vice versa, as we said. So first of all, let's talk about computation. Computation has already got there, done that. Computation is a specific thing. I just slammed together the slide. So please, if you're a computer scientist and you don't like the formal description, really a computation is a way of practically implementing the abstraction of an algorithm on some hardware. You could do it with a pencil and paper. You could do it in your brain. But it requires functions, it requires data, and it requires it to be unambiguous. Everything is explicitly described. It's not like talking to somebody in England sometimes, where you ask them a question and they'll give you an answer, but you still won't know the answer to the question. There's a little bit of ambiguity. So the way that we remove ambiguity is by having a concrete abstraction. If you go to the a computer, I'm going to keep calling it a computer, but if you go to a computer, you start with the idea of having some hardware, with some transistors, which are analog actually, and then by adding on a criterion that if the voltage is going up towards maybe, I don't know, say 5 volts, that's a 1, and if the voltage is going down towards, say, 0 volts, that's a 0. Okay, and built on that, you can then make logic gates. And on those logic gates, you can make integrated circuits and components and an architecture, which you can then lay on an operating system. And then, hey, presto, before you know it, you're playing, I don't know, Minecraft in that abstraction. The abstractions already exist in chemistry. And I think that you're going to hear about this in terms of reaction planning and forward reaction planning and so on, from if you haven't heard already from many more qualified people than I have been working on it for many years. But you can take a molecule and break that molecule up. You can break that molecule up in such a way, doing retrosynthetic analysis, you can then say, okay, this is crudely what I need to do to go forward. And I might even be able to give you some literature precedents so you have some idea of the conditions, so you can click together your building blocks and you can make the molecule. But here's one important thing that no one has yet solved, beyond having a very precise set of narrow chemistry well-defined. There's no physical instantiation in a physical system. That means if you pick up a procedure that from the literature tomorrow, there's no way you can encode that and explicitly do it without quite a lot of work, many months of work. And that kind of troubled me, because I wondered if I could just, for me, chemistry is not magic. It is science, right? But there's tacit knowledge that maybe have been hidden, not on purpose, but by the training of the chemist. And I'll explain a little bit about that. Maybe there's some questions there. So I want to introduce now the concept of a chemical state machine. A chemical state machine is just a machine that does chemistry, and the chemistry happens according to the state configured into the machine. But let's figure out how we design it first of all. Let's look at the traditional way of doing chemistry. First of all, you might take a written procedure, you'd interpret that procedure. That interpretation is a function of your expertise. So if that written procedure is missing something, or something is obvious, you will naturally do it. And that knowledge is not encoded in the procedure, is encoded in your past training, okay? So you interpret it, you do your experiment, you get your result, and you update. You'll adapt and improve it, and you might even put your results in a PDF or a CSV, and we won't be able to search it properly, but but there's a lot of data out there. But the data is very loosely coupled to the procedure, okay? And that means that you can't necessarily guarantee you can reproduce that data with that procedure. And I think that's actually quite an interesting problem that we are now challenging ourselves to solve. Let's take a digitized approach. Now you have a procedure code. You'd have a graph of your hardware. That is, on the graph, I'm going to talk about the graph in 3 senses today. I'm going to talk about an abstract graph, which is a kind of applied to the concept of computation. I'll then talk about a concrete graph, whereby I will then label the graph with modules and objects that you would recognize. And then there's an operational graph that basically is just a drawing of your fume hood with you moving around it, or your robot, where the gantry is, where the robot arm might be, or the pump. And so the nodes on the graph will be where the modules are, the operator, the reactor, and the edges of the graph represent a path for you to move stuff from module to module. So don't be flummoxed by or confused by the graph. The graph is just a description of your resources relative to each other, an indication you need to move stuff. So anyway, you've got your code, you've got your graph, you compile onto the graph, you compile them together and you get a result, and you can adapt, improve, and do version control. So you can have a software Git, a repository for chemical code. So now suddenly, let's just say Tim has just discovered the most amazing reaction under with a catalyst or added in the right way. He could write that down in his code, and that he got from Factor, read it out, and I could go to his chemical GitHub, take that code, and then in principle, if I knew what hardware he was using and graph, I could just run it and reproduce it. It would be awesome. And so what we need to kind of do is imagine how we have a chemical code repository that is actionable in any system, not a database of reactions, a database of how to cook the stuff. That's my version of this. Of course, there's lots of automation out there that can do this, and I would compare them with single-class computing machines like the Abacus, the slide rule, difference engine, whether you've got a DNA synthesizer or a peptide synthesizer or a carbohydrate synthesizer. These are beautiful things, but they are normally limited to a single class of chemistry or single class of processes. If you've got a fixed kind of bed system, not a problem. It just allows you can only do a subset of everything, and so you have to plan for that. So let's make the foundations of the computer clear. So what do I mean in the computation? What does computation really say? Computation is merely the following. Like computation, being running an algorithm to produce an outcome from a calculation. Computation is just the process of taking a code and some reagents and operating on them to produce a product. Okay, and this is a conceptual process, and that conceptual process, in the same way a logic gate, a NAND gate needs some transistors wired together in the right way, computation requires a reactor. That's number one, abstract object. That's where the reaction occurs. Number two, it needs a workup, right? It could be in the reactor, doesn't matter. You can have a special workup place. Then you need a separator, and then you need a purifier. And if you're doing reaction, workup, separate, purify, you do that once you've purified and got your product, you may want to do a second step synthesis on your product, okay? And then your product becomes a reagent, so it then becomes recursive. So you have this idea where suddenly you've got this unit, this transistor for chemistry, which just has 4 operations: react, workup, separate, purify. So what we wanted to try and do is figure out, well, and we figured this out, and we realized that if you've got this 4 abstractions, then you could have a lot of chemical processes, and such as what's represented here on the screen, adding reagents, quenching the reaction, doing filtration, evaporation, crystallization, and you could then make this universal in terms of the encoding. So you've got the abstraction comes down to the processing, to then the machine operations. It's a bit like thinking about doing Minecraft, or building your thing in Minecraft, then happening in the software layer on the operating system, and then on the actual transistors. You aren't going to go and poke the transistors by hand. You are going to use routines and so on. And that's really the power of computation. The power of computation is to reuse routines. You're not doing the same thing again and again by hand. So how can we instantiate that? Well, we have to have a chemical state machine, chemical synthesis state machine. And we, as I said before, you input the graph and the code, and it should run, and you get your product out. So let me give you the first example when we had a go at doing this. So this is a computer that we built, and the 4 abstractions are, or the 4 points we'll go through. So before, we've got that here in the very first one, we just did a fairly crude preparation. But then we're going to do the first thing now, do the reaction, okay? And where the materials chucked into the reactor, and then the reaction will occur. And it's important to say while you're watching that, I designed the computer around a batch methodology, because state machines work in batch. But it's very easy to go to flow because you just increase the frequency, okay? So here we've got the workup going on, the separation, and then the workup, and then we'll get to the isolation as we're pumping it over to the round bottom flask, to the evaporator. And then from the evaporator, we take it across. In this case, we do crystallization, to do the purification, okay? And this kind of embodies that abstraction. And so what we're able to do is kind of take this modular system, construct this device, and because the pumps and valves had network addresses, I could put them on a graph, okay? And in this case, we were able to produce, I think the first example we published a few years ago, we made nitol, refinamide, and sildenafil. And what I show here is a number of lines of code and the operations and time. So in this case, lines of code that had to be produced by hand. So the organic chemist was saying, well, thanks, Lee, you've taken away my fun and you've made me write a load of lines of code. You know, it's not fair. You know, well, they didn't actually say that, but there was some criticism that, you know, you take the beauty of in the lab, and I say, but it's labor saving and modular and universal. But now the chemist has to write code, and they're in front of a computer all day. So there were questions about, okay, we've got this state machine. It's almost like when the first computers were built, these mainframes, they were delivered without operating systems. And I knew, rather than building the programming language first, which I had done, but my group told me they didn't want to use it because they didn't want to be like literally slaves, quite rightly, that they wanted automation to use the programming language to run on. But anyway, I'll come to that in a moment. But we've got lots of different modules now for the system. high throughput modules, or I call them medium throughput modules. I think people here would define that better. We have a Computer line. We have photochemical systems. We have mini systems. We have medium throughput. The high throughput stuff is coming. We have a portable one that you can literally put in a suitcase and could make the Pfizer vaccine actually. And we have a purification system. Okay, so we've got this hardware. I've talked about computation and the abstraction. I'm going to spend the rest of the talk talking about two more points: the programming language and why it's important, and then some platforms and some results before I hand to questions. So in constructing a programming language, it's really important to understand that current computer programming language has some really important properties that are related to actually to grammars, okay? In that if you have a regular grammar, you could kind of make that, say that's rather equivalent to a finite automaton. And if you then go up a level, you go all the way up to a Turing machine. Now, what is special about a Turing machine? Well, we need computation is like computation, it's Turing complete. That means that any chemical robot that can do computation can, in principle, make any molecule. And that's why we have to be careful to make sure that our programming language is fully enumeratable and expressible all the way up to that Turing level. And that may seem really kind of esoteric and confusing, but if you want code built in my lab to work in your lab, in any other lab for that matter, we need to make sure our robots can talk to each other. The reason why you can all run software on different platforms is that digital computers are, in principle, they're not perfect Turing machines because they don't have unbounded memory, but they're good enough, and you can always write an emulator. So, and it'd be cool to write emulators for different robots. So, you know, I think one of the other speakers, Alan Asprey, we're writing a robot emulator for one of his robots, and then Jason Hein, we're writing an emulator for one of his robots, and Marty Burke, and also in Berlin at the Center for Materials Research, we've got an emulator on one of their robots, and well, actually was one of our robots and one at GSK. So you kind of get the idea that we want to go for universality. To do that, we needed to make an alphabet, right? Organic chemists, we needed to take the alphabet and make it typable. So organic chemists have already made an alphabet. We're already making rules. We already know how to construct words and sentences, but we're still copying them by hand. It's a bit like, you know, when the first Bibles were put out there, they were all handwritten and copied. So, you know, the most prevalent book before the printing press was the Bible. So we need to change that. So we needed to make a system where we could literally have a chemistry hello world. So we can go from punch cards, from assembly to something as simple, or not, maybe you wouldn't be, let's not call it simple, but it was accessible as a scripting language. So to do that, we had to then realize that we had to have a kind of development environment whereby what we started to do is just literally using natural language processing, read the literature, very similar to IBM's beautiful RxN software, and populate the boxes in our abstraction. But what was different to IBM's beautiful RxN focuses on being really good at natural language processing. We focused on trying to be really good at making the right abstraction. So you're inserting the right values and variables in the right boxes because our abstraction is concrete. And so to do that, we had a reader and we had our KDL kind of firmware that we knew would run on a processor. And then we have a virtual machine and we compile to the graph. And this diagram here kind of is rather complicated, but it shows this idea of going from a natural language processing all the way down to a representation in KDL. But I'll skip this and we'll get to the little movie that shows it working. Just at this point, I should pause and say that earlier this year, we published a paper that showed you could that use KDL in a primitive sense in a computer, and we could do cross-coupling reactions. We could make peptides, and also we could make diazurines, all in the same robot, all using the same hardware, no reconfiguration by hand, pretty much. I mean, of course, my team optimized certain parts because we had to play with air-sensitive issues for the MIDA chemistry, and then also a solid phase issues, say doing peptide synthesis. But in principle, same hardware can do all the chemistry. Here's a little a view at some of the concrete abstraction here, where you've got the input, reaction, workup, isolate, purify, and the KDL is showing up here on the right-hand side. You can see like add reagent, glycine on resin, and give amounts, and you can see the actions that are abstractions are tied. Okay, that's important. I've talked about natural language processing, so I'll skip this and I'll just go to the actual video in a moment. But I want to make a quick point before we get there to say that what we've got right now is this very first go at programming chemistry. We've made a programming language called KDL. KDL stands for Chemical Description Language. It is available now. You can if you go to kdlstandard.com, kdl-standard.com, documentation is there. If you go to chem-kdl.com, the code is there. And the good news is that Tim's beautiful new company can use our code for free. There's no commercial clawback. One of the things we're trying to do is create a HTML for chemistry, because we're in the hope that one day that people will start using KDL, will be able to change KDLs and say, oh, you've made this molecule in your robot, great, here's a KDL. And then as long as you've got a binding from your robot to your graph and so on, the KDL will run on your robot. What's coming next is KDL2, which is now goes from a description language to a full programming language. It has the complete power of a Turing complete language, but it's basically going to be backwards compatible with KDL1. And we also have a KDL database for the automatic synthesis of molecules, which we're going to be publishing soon, along with a whole bunch of molecules that we made during lockdown. The computers were socially distanced. We went walk at all the my group, the organic chemists in my team who were locked down do. Well, we actually converted the literature to KDL and validated it later to make sure we could really make virtually any molecule in our robot. So let me give you a quick example of how this would work. So let's go to literature. Just take I should say here before we go further, this is now the reason why we made some natural language processing is we wanted to remove the burden of having to code explicitly. So what I wanted to do is say, no, you don't have any knowledge of Python or, I don't know, your favorite programming language that scares you. Maybe it could be Lisp or COBOL or Fortran or something. But let's make this completely code independent. And the first step, all you need to do is go to your lab book, your ELN, the literature, copy the prose. It could be in any language if we've got the right translator built in. We did one, I think, we were seeking to do one in Mandarin. We did do one in Mandarin, actually, that we didn't release it yet. But anyway, let's go on with the English one. So we've now put in some text. We translate the text. The text in the IDE then gives you a series of actions, your procedure, you put in your KDL shown up here. Okay, and then we can then correct them. And this is really important because you wouldn't machine learn the literature and run it in your lab without checking it, because if you've got the literature wrong, you've got a lab on fire. So this allows the expert organic chemist to say, oh, no, that's wrong, that's correct. And you then check it's all beautiful. You then have your graph of your robot, you load it in, got your graph, you have your code, you compile them together, and then you've got a working code, and then you can simulate it to check that the molecule indeed works. Okay. So that's kind of where I am now. As I talked in the first part of my talk about the need for a universal kind of robot that could do computation. And the reason why I built the robots was that I do love building stuff and I do love engineering, but I could only think by building. And actually designing the abstraction, I could only manage it by actually building the robot with my team. And I insisted for a long while that we had to have, power over Ethernet pumps and valves because they needed locations on the graph, that we needed to minimize the number of USB daisy chains because I needed the thing not to crash. I needed my graph to be robust, because if the graph wasn't robust and crashing, then you'd have another incomplete robot that wouldn't work. So what I'm going to do now, and then what I did is I talked about the programming language and how now the programming language is really about the implementation of the abstraction, and we've gone really high up to the chemist now. We've met the chemist fully, chemist does not need to program in Python, although a little bit would be useful if you're a developer. And I think that's coming across in probably a lot of the talks. So let's talk about various platforms. So one of the things we're doing right now is making a really high throughput version of the computing system. And we're also going to have a view of going to very, very, very high throughput multi-well plates, microfluidic system. But before we go right to that incredibly kind of miniaturized system, I want to see what can I make when I'm going sub-bench scale, but not all the way down. Because I'm curious about what we can discover when we don't know anything about the system. And so you can see here a graph of lots of inputs, a rack, and we're doing this for our drug discovery computing system that we may or may not, I'm not going to talk about today. The reason I'm talking about it today is it's still in development, and I want to make sure that the video that's being taken is going to be accessible to everybody. But I'm going to now close by talking about a couple of things. So we've been, in my lab, we've been trying to explore reactivity in its most general sense, to take our liquid handling system. So you imagine now we've got the liquid handling system, we know where all the modules are, they're on a graph, we have KDL, which can now it works in a process space, like move reagents, add solid, add catalyst, heat, cool, shake, sing magic song, whatever you need to make your compound crystallize. It can all be rigorously encoded. What I want to then try and do is say, well, okay, rather than just making known stuff and checking it at the end manually, could we use inline spectroscopy and build an AI? In this case, just use a neural net trained on some NMR to basically search chemical space. And the idea would be to give the robot a whole bunch of reactions, and then the robot would basically do these reactions. And in this case, we paid attention to in this slide here, you can see the NMR down in the photograph and the mass spec on the side here, and this kind of massive mess of pumps and valves. This project was running at the same time as the computing project. So it was one project where basically it was all I'm going to call them hippies, because some in my group, I mean, they're brilliant, but there were people constrained for the computer, so modularizing stuff, and people doing exploration. And this rig was initially built by a very talented individual who's now Jaroslaw Granda, who's now in the Institute for Organic Chemistry in Poland, and I'm watching with a kind of anticipation of what he's going to do. He's a genius, and he put a lot of this together with Dario Carmeli, who's still in my group at the moment. And basically the idea is to search chemical space and use NMR and mass spec together to find new things. When Jarek first did this, we used a slightly different classifier, but now we built on this and said, well, look, what we'll do is we'll just use a fairly reasonable neural net where we have a convolutional network that uses max pooling and then concatenates the whole kind of the NMRs in such a way that we can discriminate reactive from non-reactive NMRs. And the crudest thing, if you've got the NMR of all the reagents and you then mix reagents together, and you can then work out what the average NMR would be if nothing had happened. And if it looks different, then you can train the neural net to recognize a reaction. Okay, and so the reagents are shown at the bottom here. We have this kind of process here, and we're able to assign the NMR reactivity, and the predicted versus expected is pretty good. But what we found that was interesting with this is that actually, when the system was doing some experiments, it came up with some pretty interesting random stuff. And okay, these are one pot, and I'm having an endless debate of organic chemists about, can we make our AIs creative? And I think that maybe the debate has got a bit lost about 3 or 4 years ago, but now the debate has become much more nuanced and much more fascinating, because most chemists are now understanding that the AI is not, the chemist is using the AI as a tool, right? You can put your creativity in the AI. The AI is not magic. It's just a mathematical process, but it would allow you to do things that you wouldn't have time to do otherwise. I think that's some of the beautiful stuff about the high throughput stuff, that you can start to really imagine the type of reactions you might want to invent, and then go and literally find if it's possible. So in this case here, I was going to show you a couple of reactions, some known products from some known procedures up at A, some unknown product from a known procedure, and then the bottom here with Tosmic, this unknown product from an unknown procedure, down here. And this was kind of weird in that we got 6 moles of Tosmic reacting with itself, basically. In this is kind of involves 6 equivalents in a multi-step single substrate reaction. You get 5 new carbon-carbon bonds in 47% yield. Now, I know everyone knows that Tosmic reacted, and yeah, it's not the most exciting molecule in the world, but it's like a massively combinatorial problem. You are not going to go in the lab and anticipate a reaction that's going to make 5 new carbon-carbon bonds based on one reagent substrate. You're just not. You don't have enough time to do all those trees, even with some of the computational power that we have. Okay, I'm just going to give you the last couple of glimpses. These are the origin of life engines that I now can build. Many years ago, when I started the Chemputer project, I went to funders and said, "Hey guys, give me some money. I want to basically brute force the origin of life and make artificial life forms." And they said, no. And I went away sad, and I went back and said, "Hey guys, I want to make a robot that does chemistry and does the boring bits a little bit better, and maybe we can make some drugs and do some molecular discovery. Can I have some money?" And they said, "Yes." So then a few years later, I'm able to use the same technology to kind of to build these robots that can do recursive chemistry. And we have to search at much bigger scales. We can't do this at a micro scale for very good reaction reasons. I can explain if people are interested. So I'd love to implement Tim's ideas, but they just won't work under these scales for very important kind of physical constraints. But you can see we've got 3 different engines, all coupled to mass specs. They're using the KDL now, a DOE KDL, which also, like Factor, can basically generate massive design of experiments. And there is a library that we're going to release very soon, so you can generate your own DOE on high throughput systems and the KDL bindings for that. So last couple of slides. I just want to end by saying the overall vision is Chemputation. We want to do it on different platforms, be it our computing systems in Glasgow, the ChemPU, the SMS in Illinois, in Marty Burke's lab, the N9, or the N9 is changing now, but all the delightful stuff that Jason Hein is doing, and also the incredible kind of power that Alan Asprew's team have got put together, their ChemSpeed and their kind of production line for new material. We want it to be task universal, so we can do synthesis, discovery, and optimization in one robot. So you discover something, you get the KDL. You then go, "Oh, that KDL optimized. I'll zoom in, make it better. Then I've got a synthesis procedure I can then give to you. You can do in your lab, and it should work." And then we also want chemical universality. You can do any reaction, and that's the idea. I'm going to stop there. Thank you very much. I think I've gone over a couple of minutes. I'm sorry about that. But this is my team in Glasgow. Last year we couldn't do a group photographs, so we did group selfies. And I really want to thank them for their work. But I also looked through the list of people participating, and I've spotted some ex-group members who've dropped by. I think Jakob might be here, Jakob Wolf, who did a very good job with a computer working with Sebastian at the beginning, and also Jarek, who's here. So I saw you guys. So thanks for coming. I'm happy to answer any questions. Thank you.
Thank you so much for your exciting talk, Lee. Yeah, we have a few questions in the Q&A. Maybe I can start, Raj?
Yeah, sure.
Okay, so a question from Nessa. Mapping between different robots is challenging. Do you have specific plans to be able to map from a computer to other kinds of robotic systems so as XDL is reproducible between them?
Yeah, yes, that's a very good question, and it's not challenging at all. It can be done easy. The only thing you need to worry about is what can your robot really do, right? What is the temperature range? What is the chemical compatibility? And then we will, if you're interested, we'll help you write KDL binding. So I maybe said it really rather badly. Jason Hein's lab has managed to use KDL on their robot, a different robot. Marty Burke has managed to use KDL on his robot. Okay, Alan Asprue is now running KDL on his robot, and then Jakob helped me build a new robot in BAM in Berlin. They kind of, I was going to say mess it up. They rebuilt it, and now we're going to be using KDL on that. And there's KDL running on robots, robot GSK. So yeah, it's basically, who cares about the computer? I mean, I care about it. It's my group's baby. There's a brilliant thing that they did. But KDL that come out of it is going to be operatable on any robot, and we have provided in our software repo the steps you need to go through to make that work. And we'll be very happy to work with anyone in an academic capacity and a commercial capacity, but academics mainly to start with, to get people trained. And so it's a very good question. And hopefully that kind of makes sense. Because it's Turing complete, it will work.
Okay, thank you. Then another question from the Q&A. How do you envision the practicality of chemical synthesis state machine carrying out multi-step synthesis with column chromatography required in the process? Also, is online analysis possible?
Yes and yes, we've done it. Raj asked to record the talk, and what I try and do is, I don't know about you guys, but I've been doing Zoom all year. And for me, Zoom is to be a replacement of me going in a lecture theatre and telling you guys what we're doing, like kind of private. But the way that this conference has been publicized to get everyone in, the maximum number of people, which is brilliant, by the way, I really think it's a great job. I decided today to not present some of those things, because not finished yet. But I'll give you a summary here. We've got a computer connected to a flash chromatography system. So it works pretty well, or you controlled by KDL. And we've done multi-step syntheses. And I think the largest number of steps we've done in a computer today is about 12. And that's pretty exciting. So both of those have worked pretty well. I think I answered the question. I think there's a second part, VJ. I'm having a senior moment. Help me. What did I not answer?
Oh my God, I moved the question. Let me double check.
Sorry.
Yeah, is online analysis possible?
Oh yeah, that's sorry. Yeah, exactly. Yeah, so we've got the online analysis we've done so far is NMR, infrared, mass spec, Raman. Okay, and there's also a whole bunch of other little secret sensors we've put on the computer for like telemetry, like running a drone, right? Like, you can imagine RGB or a sound or another stuff. So yeah, thanks, VJ.
Well, there's a comment from Tim. Awesome talk, Lee. And
thanks,
another
Tim.
question. I wonder if your computer can reliably handle unexpected, highly exothermic reactions or other emergency situations so as to avoid explosions.
Well, I mean, in some way, I want explosions in the computer rather than explosions on the bench with a human. And so we're making the alchemator, which is KDL in a nuclear reactor to do alchemy, right? Because it was like, wouldn't it be batshit crazy to do that? But coming back to the question, so yeah, so we've got a computer vision system, and in the computer vision system, it sees any motion, it pushes the off switch. That's the plan. The other thing that we're doing right now is, we do have a system, and again, I've got my team working on it at the moment. So a really good PhD student, Alex Hammer, and postdoc Artem Leonov made a self-optimizing computer that controls exotherms, controls some unexpected stuff to do optimization. It doesn't do everything unexpected, but what we will have in the KDL is we'll say reaction should do this. We expect the temperature to be here. If you see them by default, like on an airplane, if you see your height decreasing, you get an alert. You see the temperature going up, it throws an alert immediately and will turn the reaction off. And the beautiful thing about that is because you're coding in the reagents, it will also point out incompatibilities and say, are you really wanting to add this oxidizing agent with this reducing agent and stuff like that? And so one of the really important things that excites me a lot about the computer is that we can go back in the lab and do more dangerous stuff again, because we're not endangering the chemist. We are making them more secure, and the person can be away from the process. And so that's what we're doing with the organometallic computer.
And then maybe a final question from me. Like in an ideal world, if the digitization of chemistry like makes huge progress, I don't know, like in the next 50 years, how do you see the role of a future chemist like in 50 years as compared to a chemist nowadays, like a PI or PhD student?
So I think that it's going to happen much quicker than that in the next 5 years, right? I mean, why would you use a separating funnel? I mean, how many times have you put, I mean, I've chucked ether over myself so many times, right? It's a bit like if you go to a mechanic now, I've got an Audi, go to the mechanic, they take a module out and put a new one in. So I think what will happen as time goes by is that chemists will still be chemists. We'll be making molecules, designing them. We'll just make more. They will be, we will make more molecules. We'll be able to go to 25 steps routinely. And look how far in chemical space we'll be able to go. You'll get more. There's just so many more possibilities. So the chemist is not going to be replaced. The chemist will be made safer. The chemist will be less bored. And the chemist will not feel they have to be in the lab so long if they've got something running. They can just run it overnight. And so I think that it's all good from that point of view. And I can't bring this future fast enough because it's not that expensive. It's not that complicated. And also it's going to increase the number of chemists because we are going to start discovering more drugs that are effective more quickly. And that is going to be amazing. And so I'm pretty excited by that. So I think my message to everyone out there is coming now. The way you can prepare is start learning about molecular identifiers, get excited about the automation and AI and language out there, and don't be too intimidated. It's a lot of hard, looks like hard math, but it's not that hard once you work at one abstract level, because these are really complicated things. But no, I think it will start happening now, and it's a really good question.
And you touched already on something I wanted to follow up on. So what do you think, to what extent like programming skills, for example, will be like commonly required as part of chemical education? Not just optional, but mandatory.
I think everyone should learn to program. I mean, I should say, I said that. I mean, I taught myself to program when I was 8, right? So I was at X81, and I used to routinely code in assembly. It's like we should make everyone do assembly and make it now. No, so what's probably more important, if someone said I've got a fixed budget of time, what should I learn first? I think I would learn a bit of more cheminformatics, molecular descriptors, a bit of databasing. So I think most important is, how do you describe the molecules? How do you then represent the data? What do the data structures look like? What do you then get from the lab? And then, of course, if you want to go into hardcore programming, go ahead. That's brilliant. But if you have those skills, you are so marketable. I mean, probably Tim is looking for people in his company. I'm going to be looking for people in my company that's still a little bit in stealth. My other company, Deep Matter, really likes to have people in the chemistry informatics interface. It's really a valuable place to be. And I think if you can learn to program there, I think it'll be brilliant. And I think it doesn't need to displace things. We just won't need to teach chemists about separating funnels anymore, because it's like telling to a car mechanic they need to measure the distance between the emitter and the collector on a spark plug. They were just like, no, why would I do that?
Okay, thanks. And I promise, final question. It just got in when I asked mine. Do you have any buy-in from the chemistry automation companies on their take-up of XDL? And had you considered the use of mobile robotics at all?
Yes and yes. So some automation companies remain very silent because it disrupts them a little bit, but not much. I think it will help a lot because they make brilliant. There's lots of brilliant companies out there, but there are some companies that make hardware, like you've seen the Bookie. Right, and so Bookie just basically just gave us exposed their API completely. So Bookie stuff is KDL compliant right out the box. So that's happening quite a lot right now. And in terms of mobile robotics, well, Andy Cooper's doing a really good job there, and I'm starting collaboration with Andy right now, where I want to put KDL on his mobile robot and vice versa. I think mobile robots have their place, particularly if you're doing solid state handling. And of course, Jason Hein and Alan and we're all connected actually with Bartosz on a DARPA grant. So we're thinking about how we can move things around doing unit operations. And also I've got some mobile robotics in my lab, but not robots or androids walking around. There's different ways of moving stuff around. And I think the chemist needs to be more, I want automation in every fume hood. I think a mobile robot's too expensive and it's really intimidating. You're going to crack, you probably won't be allowed in a lab with a mobile robot like in Andy's lab. I think or you'd have to coordinate it. So my mission in life is to make it programmable and put automation in every fume hood. And the automation should cost really no more in the end than the price of the stirrer hot plates, which are not cheap now. They're $800, right? The rotary evaporator. And then what I think will happen is that people will swap KDLs. And if there's a marketplace in KDLs, then we won't be going to publish in Chem first. But don't worry, we will almost first. I will be basically going, wow, I just made this new molecule. I'm going to put it on Chemify. Someone will download it and make it work, right? And then, and maybe the publishers might demand that the KDL has been validated. And so there is a really good opportunity for publishers and database people and the chemists to work together to have the open data. And the final thing I'll say is if you're using a bit more automation where everything fails, you can just collect that failed data and publish it and say, and as long as you can anonymize it, maybe you can anonymize it and say, because everyone will look at my data and say, oh my God, Lee is the crappiest chemical programming person in the world. Look at all this shit. But if you could anonymize those conditions, wouldn't it be great if someone said, oh, I'm gonna do this reaction, and then someone could look at Tim's data and my data and maybe someone else's data and say, oh, they've done that before. Okay, Cronin, probably we can do it again because he's an idiot, but Tim's not an idiot. We're not gonna do that again. And so you can then make the judgment on the data that's put on the cloud, and that would be a beautiful thing to happen as well. So I think keeping away from mobile for me for the moment, because I want to concentrate on making sure everyone has access.
Okay, thanks. And I'm glad that you're still considering to publish something in Chem.
I'm trying. You know I'm trying.
Yeah, that's why I'm saying it, yeah. Okay.
Thanks.
Yeah. Thanks for the exciting talk, Lee, and the very, very helpful QA. It was a great pleasure to see you again and to host this session with Tim and you. Thanks for the organizers to giving me this opportunity, Raj, Ben, and the whole team. And yeah, I think I'm going to hand it over to Raj now for some concluding remarks.
Yeah, thank you so much, Vijay, and Lee and team for this really exciting talk. And I'm sure that all of our attendees has really enjoyed, because I can still see more than 200 participants at the end of the day. So we'll be back tomorrow the same time, and please make sure to write us if you feel that we should change the way we are running our program currently. If you have any better suggestion to do it, you can send us an email or even tag us on Twitter. And those of you who don't know that, if you come up with a really good suggestion, we have 3 Twitter prizes, and thanks to our sponsors, that's why you can do it. And our registration is still open, and I keep stressing on that fact because we still have nearly more than 25 speakers who will be speaking for the next 4 days. So if you have any friend, any colleague, or even any student who could be benefited from this program, please make sure to inform them and encourage them to attend this talk. And with that, I would like to conclude today's session and see you tomorrow. Thank you so much.
Thanks. Good job. See you later.
Thanks.
Good.
People are already left. They're not in front of the program. Let's close the program. We'll chat later.